Particle equilibrium is synonymous with force equilibrium. Sum of the forces as vectors equals 0. It will be easier to illustrate this first in 2 dimensions, so we begin with 2-dimensional problems in section 3.1. As part of this process, we introduce the concept of the free body diagram. The free body diagram is a graphical representation of all the loads acting on a particle or body, and is a crucial first step in understanding equilibrium. A quality free body diagram is an important precursor to writing an accurate set of equilibrium equations. In section 3.2, we take some time to introduce additional mechanical elements. We have already talked a bit about the difference between woven elements like cables and solid elements like bars, but we will revisit this topic and also discuss coiled elements like springs. We then transition back to equilibrium, examining some 3D problems. Finally, we close with a discussion of design issues in structural systems. As mentioned at the very beginning of the course, the field of mechanics is based on a set of relatively simple laws inferred from observation. The first law is that a particle experiences no acceleration if there is no net force acting on it. The phrase, "a particle remains at rest or continues to move in a straight line with uniform velocity," indicates an absence of acceleration. How is this? Acceleration is the time rate of change of velocity, which we could write as acceleration equals dv dt, where we've represented v as a vector. Since v is a vector, we could write it as a magnitude on a direction. So we could write this as d by dt on the magnitude of the velocity, which we call the speed, times a unit vector that points in the direction of the velocity. Using the product rule, we could write this as rate of change of speed with the direction remaining constant plus constant speed with a changing direction. This tells us that acceleration can occur from a time rate of change of speed with no change in direction, or a time rate of change in direction at constant speed, or some combination of the two. This also tells us that there are 2 ways of not accelerating. The more obvious way is for the particle to be at rest, so v is simply equal to 0. But if the particle is traveling in a straight line, no change in orientation, at constant speed, no change in magnitude of velocity, then the time rates of change of speed and orientation are both 0, and the particle is also not accelerating. The significance for us is that a particle doesn't actually have to be stationary for the equations of static equilibrium to be valid. Although many of our applications will involve stationary objects, the equations of static equilibrium still hold if the object is in motion, as long as its motion is no more complicated than traveling at constant speed in a straight line. The second law expands upon the first law by providing a quantitative relationship between the net force and the acceleration. The force required to achieve a given acceleration for a particle of a given mass is the product of mass and acceleration. Alternatively, the acceleration experienced in the presence of a given net force can be written as 1 over the mass times the force. Mass m is a kind of inertia, where inertia can be thought of as resistance to change. Specifically, mass can be thought of as the resistance a particle offers to the acquisition of linear motion. This is as opposed to other kinds of inertia, to be discussed later, that represent the resistance a body offers to the acquisition of angular motion. The final and third law indicates that interacting bodies experience equal and opposite forces. This will be especially important for us as we take structures apart to investigate how loads are transmitted between interacting components. Suppose we have a member that's part of a structure and we want to cut into it and observe what's happening between the two members. If the structural element supports just axial forces along its length, then whatever happens on this side in the axial direction has to be matched by this side. The forces interior to the member are equal and opposite. It isn't necessarily true that the forces have to be along the axis of the member. In addition to these forces, we could have force components transverse to the axis of the member. If we have a force component in this direction, for instance, it has to be matched by one in the opposite direction on this side. In 2 dimensions, static equilibrium of a particle requires all force vectors acting on the particle to sum to 0. When resolved into mutually perpendicular directions, this vector equation can be represented as 2 independent scalar equations, as indicated here. Before writing these equations, we have to first identify all the forces acting on the particle, a process that is facilitated by the drawing of a free body diagram. There are 3 classes of forces that act on a particle. First are those forces from the environment, which we will refer to as external forces. Second, forces that arise from separating the particle from its surroundings. This often involves cutting through structural members attached to the particle, and in doing so exposing internal forces within the member. Third, forces that arise from separating a particle from supports or points of anchorage to something massive. This could be a floor, ceiling, or wall if the particle is small, or the earth or soil if the object is large. These are called support reactions or just reactions. The procedure for drawing a free body diagram includes these steps. Well, first, we'll decide on a particle to isolate. Sometimes this is obvious. In other instances, and in examples to be seen shortly, the particle is a joint between intersecting structural members. In such cases, equilibrium of the joint imposes a relationship between the forces of the structural members intersecting at the joint. In complicated assemblies, points of intersection of interacting members are often of interest. Second, imagine that the particle is cut completely free from its surroundings. This process of separating or isolating the particle is what puts the free in free body diagram. It may be helpful to draw a closed line around the particle of interest. This enveloping contour could be as simple as a circle, but it need not be this simple. The important feature is that it be a closed, non-self-intersecting path. No figure eights or other overlapping lines. Third, we put a point on the page to represent the particle. And then fourth, we identify and sketch all the forces acting on the particle, including those that develop in the process of isolating the particle from its surroundings. The latter include internal forces, where the isolating cut passes through a member of the assembly, or support reactions, where the cut passes through a point of anchorage. Forces that are not included in the free body diagram are those that are actually interior to the enveloping surface. That is, if we have internal forces that are acting between members of an assembly that are not actually cut through as part of the isolation process, we don't include those forces. As you are drawing your free body diagram, make a note of which forces are known, a weight for example, and which are yet to be determined, and give each currently unknown force its own unique symbol. Finally, select an orthogonal coordinate system to serve as the basis of the scalar form of the equilibrium equations. You may want to annotate your sketch with angles, rise over run symbols, or other important information to facilitate decomposition of the force vectors into these mutually orthogonal directions. Having done all this, you are now in a position to write equilibrium equations with the free body diagram as a vehicle for writing those equations. In our first example, we have a relatively simple assembly consisting of a single cable AB and bar AC. Although bars, cables, and other structural elements have weight, their weights are typically negligible compared to the other loads they support. There are exceptions to this, but for now, we neglect the weight of these elements unless instructed to do otherwise. The other important feature of this schematic is the anchorage points at B and C. The small black dot is meant to indicate a pin or shaft that penetrates a pair of flanges that are then anchored to a wall. The light D-shaped outline indicates a flange, and the cross-hatching indicates a rigid type of attachment, bolted or welded to the wall. The significance of the pin is that it permits the structural element to rotate freely about the pin's axis perpendicular to the page. The combination of the neglect of self-weight and the presence of pins implies that the bar carries a load only along its length, and this load is uniform throughout the bar. This kind of member, in fact, is called a two-force member, and we will discuss it further in Chapter 6. We also know that the cable can only carry a tension along its length, and the neglect of its weight also implies this tension is uniform. Now consider the first step in our process of drawing a free body diagram. Namely, what should we isolate? We could choose to isolate a section of either cable or bar, but that wouldn't be very useful. The cables experience uniform tension, although we don't know yet what that tension is, and the bar experiences uniform compression. We don't know what that is yet either. It is far more useful to choose to isolate the joint at A, where AB and AC are pinned together. So we'll draw an enveloping surface that cuts through the cable AB and the bar AC. In preparation for drawing our free body diagram, we note that we have one external force in the form of the 100 Newton load, and we're also cutting through members AC and AB where the enveloping surface passes through those elements. We'll draw a point representing A and sketch portions of elements inside the enveloping contour. Here first is our 100 Newton load. And now I'm going to have an internal force in both member AB and AC. To emphasize that I've cut through a member, I'm going to draw a little squiggle here that indicates that that's where the enveloping surface passes through. I don't have to do that, but it helps remind me that I have an internal force that develops there as a result of that enveloping surface. The cable AB will be in tension, and I'll draw it as such. So here is a tension in AB, and it's aligned with the structural member AB, so it's going to make a 30-degree angle with the horizontal axis, as I've shown here. The member AC is going to be in compression. We'll see that shortly, and that's going to give it an orientation that looks like this. Again, this acts along the geometry of the member, so I'll call this the compression in AC, and it's going to make a 45-degree angle here with the horizontal. Finally, I'll annotate this with just a traditional XY coordinate system, and that will form the basis of my writing my equilibrium equation. Note that tensile members exert forces at joints that tend to pull the joint apart, while compressive members exert forces that push the joint together. The X and Y force component equations that follow from this free body diagram are as follows. If we write sum of the forces in X equals 0, we have TAB cosine 30 minus CAC cosine 45 equals 0. In the y direction, we have TAB sine 30 plus CAC sine 45 degrees minus 100 newtons is 0. We'll call these equations 1 and 2. Using the fact that the cosine of 45 is equal to the sine of 45 equals 1 over root 2, we can add these equations together and the term involving CAC cancels out, leaving TAB cosine 30, which is root 3 over 2, plus sine 30, which is a half, minus 100 newtons equals 0. So I'll just bring the 100 newtons over to the other side. And that gives me, if I just divide by the term in parentheses here, that gives me TAB is equal to 73.2 newtons. Back substituting this result into the first equation gives us the compression in AC is equal to TAB times the ratio of cosine of 30 to cosine of 45. And using the value for TAB, that turns out to be 89.7 newtons. The fact that these numbers turned out to be positive tells us that we represented each force correctly in the free body diagram. You might be saying to yourself, what if I didn't know that member AC is in compression? Wouldn't I get the wrong answer? Actually, you would not. Let's play it out and begin by redrawing the free body diagram and see what changes. Here I've resketched the free body diagram showing both members as being in tension. Writing my force component equations in x and y now produces these expressions. You'll notice that the only thing that's different between these equations and my first set of equations is that the signs associated with member AC have now flipped. Still, adding those equations together, I'm going to get the same result that I had before. The terms involving TAC will go away, and adding them together will still give me TAB is equal to 73.2 newtons. Now, if I back substitute this into the first equation, TAC is equal to minus TAB times the ratio of these cosines, gives me the same numerical value, it's just negative. But a negative tension is a compression. So there is no difference between reporting a tension of minus 89.7 newtons and reporting a positive compression of plus 89.7 newtons. There is no difference between these results. This is important because as assemblies of members become more complicated, it will become progressively more difficult to see, by inspection, the direction that forces act. With few exceptions, we need only represent the presence of a force and then let the algebra tell us whether or not we guessed correctly. If all the values turn out to be positive, as they did in our first version of this problem, it indicates the directions represented in the free body diagram were correct. If some turn out to be negative, it indicates that those that are negative actually have the opposite sense to what was represented in the free body diagram. Here we have a second example that looks very much like our first example with different angular orientations. Once again, the joint between the two members AC and AB will be of interest, so we'll draw an enveloping surface around A. Once again, we have our 100 Newton load, and we're then going to have two internal forces where we cut through these two members, AC and AB. The cable at AC has to be in tension, so I'm going to represent it that way. And then it will turn out that the bar AB will be in compression, so I'm going to represent it that way. We'll annotate this with an angle in our XY coordinate system, and then we're ready to write our equilibrium equations. In Y, we have TAC sine 20 degrees minus 100 newtons equals 0. We can solve for the tension in the cable directly, and that number turns out to be equal to 292.4 newtons. And then if we back substitute that into the first equation, we get a compression in AB that's equal to 274.7 newtons. Note that the magnitudes of these loads are about 3 times higher than the values obtained in the previous illustration to support the same 100 Newton load. The presence of a shallow angle with the horizontal represents a very inefficient way to react to vertical load. Since every structural element has a failure load, we generally want to minimize the load each element carries when we configure supports to carry a given load. Choosing a cable bar configuration more like the first illustration, where the vertical components of supporting members are larger, is preferable to choosing the much flatter configuration of this example.